Okay, so in this session we are looking for a multi-species analysis. Okay, so first let's discuss about the problem statement. And so this is our problem statement. So in the previous session we discussed about a laminar flow and turbulent flow on a piped section, but this problem is much complicated while comparing to the previous examples. So here we have a car carriage. So in this car carriage we have a car and a jet fan. So basically what happened here is, so in this car carriage there is a fire accident. Okay, a fire accident has happened. So due to the fire accident, enormous amount of heat, a hot gas that is about 1200 Kelvin gas is released from the engine region. So it mixes around the atmospheric air, that is oxygen. So we have an outlet and also an inlet over here. So from this inlet a fresh air comes inside the carriage. So we have a jet fan also. So this jet fan will sucks the air from the inlet and forced, which blows on the hot region, and the combination of this air will get out from this outlet. Okay, so likewise we solve the problem by using symmetry condition. That means we have a same area on the opposite side also. We only model on one side only. Okay, so due to this combustion, what's special in this multi-species analysis? What is multi-species first? Okay, so multi-species means we have a multiple gases. Okay, so in the previous stage we worked on solids and fluids. So but we only work on a single fluids or single solids. Okay, so if you have a combination of a lot of fluids like N2, O2 and carbon dioxide and H2O vapor, so we call it as a multi-species. Okay, so in this condition, in the atmospheric we have a mixture of air like N2, O2 and CO2 and H2O. Okay, so everything they have given over here. Already we have the pre-processed designing file, so we are not interested to design these things. So it's very simple to design by using design modular or some other design tool. So you can create this structure by using surface, and all you need to do here is you need to assign the boundary conditions. So as we mentioned over here, so this wall is act as our symmetry plane and this is act as our inlet fan, inlet, and this is our jet fan and this is our heat region. So from this wall, from this side, the heat energy, that is around 1200 Kelvin. So as we mentioned over here, so the H2O and CO2 gases released from this end. Okay, so this is our outlet. Okay, so what we do is analyze the release of heat and combustion gas from the car, so within the engine fire in a ventilation parking carriage. Okay, so that is our first aim, and simulation will run at steady state. So this entire analysis is, we're going to assume that as a steady state one. So the fire has reached at a stable stage. Okay, so there is no sudden blasting or it doesn't happen. So the fire is increased stably. Okay, so that is why they mentioned as it is a steady state condition. Okay, so apart from that, everything they have given like the momentum, so the speed of the jet fan, so they given that 80 Newton per meter cube, and 6 meter exhaust and inlet velocity, everything they have given. So what we're gonna do here is we just open the Ansys Fluent CFD module and just import that pre-processed file. So that includes the geometry files as well as the boundary conditions like jet fans and then fresh inlet. So it is already created one. So we call it as a pre-processed mesh file, so which is in the format of MSH. So I have attached this file in the description. You can also download this file and try it yourself how to do this analysis. Okay, so let's start this analysis. Okay, so like always we have a component system as well as analysis system. So I'll just drag and drop the Fluent flow Fluent. So once you drag and drop that, so we don't create any mesh, geometry file or mesh file. So we already have that MSH file, right? So I just click on the mesh, right click. So you'll have the option to import the mesh file. So just click on that. So my file is actually take places over here. So I just click on this file. So now it is get imported. So you can download this file from the description, so as I mentioned in the before. So once it is imported, so now it is changed into now the geometry and mesh is changed into imported mesh. Okay, so just double tap on the setup. Now the Fluent module is get started. Since it's a 2D, if you want to increase your probability of convergence, you can just enable the double precision option. So however, it may increases your solving time, so that is not an issue. So the convergence is the most important thing. So I'll just enable this. So the remaining options is for the server setups. So we don't have any servers, we are working in a single system. So I'll directly click on start. Fine. So once the file is get imported, and then Fluent needs some times to get load the mesh file. Now it's get loaded. You can view our boundary condition is already applied. Okay, so this is our entire geometry, but it looks something different because it has a wall on the ceiling as well as the sides. Everywhere it has the walls. Okay, so to view this diagram much more clear, so right now it's set to phases. So you can change the display option. So how can I change, sir? It's very simple. So here you have the option called display, right? So in the general panel. So you know about these things. We already discussed about this thing in the earlier classes. So I'll just click on display. So once you click on the display, you may have a varieties of options. So by default it's set to phases. I'll just uncheck this and just click on edges. So when you check the edges, make sure your edge type should be outline. Okay, and select all the things. By default it's selected all. So once I click on display, now you have a line frame mode. Okay, so it's much easier to view the diagram. So this is our inlet. So from this way the fresh air is get entered into the garage, and this is our outlet, and this is the air, that is hot air is comes from this combustion region, that is from the engine of the star. Okay, so now let's start to assign the boundary condition. So when you click on this, set the display views. So after that you need to check the mesh. Just click on check. Make sure all the meshes and then volumes are in the positives. So if you have any negative values, that may be a problem in your geometry. So you have to recheck it out. Okay, so once it is done, I'll move on to the next thing, that is viscous setting. So just double tap on the model. You'll have a varieties of option. I will directly go to the viscous. So here we don't have any turbulent flows. So this flow is completely a laminar flow. For this problem, I'm going to use K epsilon 2 equation. So I'll choose K epsilon and I'll set the type to reliable. So once I set the reliable and say I want to view the results more clearly in the walls, I'll choose enhanced wall treatment. Okay, so I don't want to disturb any other things. I just leave to as it is. Once you change that, just click on OK. Now the viscous condition is get changed, and in this condition we are also involved the species. See, there is an option which is related to species. See here. So in the previous problems we don't get disturbs it, but in this case we have a varieties of gases like NO2, N2, CO2 and H2O, vapor. Okay, so how can I define? For that you need to enable this option. So then only you can define that material, that the mixture of material in materials, that options. Currently when I click on the materials, there is no option called mixtures. So only fluid and solids is available. So but when I enable this option, just double tap on the species. I'll change the type to species transport and make sure this option diffusion energy source is enabled. And when you choose this option, by default you have a mixture property. So if you want to change the name, you can change, but I don't want to change that. So I will leave as it is. When you select the species transport, just click on apply and OK. Okay. So when I do that, if I double tap on the material, you may observe that there is a new thing is available now. That is mixture template and nitrogen, oxygen and water vapor. So it's a very basic elements. So by default it's added. So if you want to add any other material, in this problem statement we have CO2, but CO2 is not presented in the mixture template. So how can I add that material? Okay. So just double tap on the mixture. Once you double tap on the mixture, you can go to the Fluent database to add any material. So in this, a CO2 is a Fluent, so I'll change the type to Fluent. So you can choose the CO2 from here itself. Just click down. So calcium, carbon. Okay, so here we have the carbon dioxide, CO2. So just select that. So this property will be displayed over here. So I want all these properties. Just click on copy to copy this property. So once you copy that, click on close. So if you want to create that, just click on create and change and say close. Now the carbon dioxide is added in the fluid, but I want to add this carbon dioxide to the mixture. So to add that material, just double tap on the mixture template. In here itself, so you can add a material by there is an option to specify the mixture species, right? So just click on edit. So in this edit, I want to add the carbon dioxide from the fluent to this region, that is for the mixture template. So I'll choose this material and say add. Now this material is moved from the fluid to this region, and say click on OK and close. See, now the fluid carbon dioxide is moved to this region. So if you want to remove from the fluid, so you can remove, or else you can just leave it as it is. So just double tap. If you don't want that, you can just select and say delete it also, but I don't want to delete it that. Okay. So once you added the mixture templates, you need to change some of the settings in the mixture templates. So I just double tap on it. So change the properties of the densities and specific heat and thermal conductivity. Okay, so I'll change the density property from the incompressible ideal gas to the, so maybe you can choose volume weighted mixed draft. So I don't want to specify the specific heat, so it's already in the mixing law. And also I'll change the mass weighted mixing law. Okay, so once everything is done, so you don't need to change this values, and say click on change and create and say close. Okay, fine. So now the mixture is defined. So once you define that, you need to add another material, because the outer wall of the car carriage is made up of concrete. So you need to specify the concrete, right? So right now by default only solid is aluminum. So I just double tap on the solid. So to create a new material, I'll rename it to concrete. CONCRET. Okay. So the chemical formula is also concrete. So you can give any symbols as if you want. So by default you don't have any material like concrete in the Fluent database. So that is why we created a new material. So obviously it's a solid one, and the density of this material is 2400, and the specific heat is 1000. Okay, the thermal conductivity is 1.2. So once you define that, just click on change and create, but make sure you are not overwriting this material, that is aluminum. So I want to create it as a separate material, so just click on no. So once you click on no, a concrete material is created separately. So if you want to overwrite the aluminum, you can also do that, but I'll create it as a new material. Okay. So now we created the mixtures as well as the solids. So this is up to our material creation process. So we need to apply the mixtures and then solids to the surfaces, right? So that is why we have the option called cell zone condition. So I'll just double tap on it. So in cell zone condition, I want to change, or I'll give the rotational velocity to the jet fan. I'll choose the jet fan. So when I click on that, by default it's set to fluid. Okay, it's fluid, right? So I'll just click on edit. Now we have a turbulence over here, that is a rotational velocity. So this region is rotated at certain RPMs, that is I think 80 Newton per meter cube, right? 80 Newton per meter cube. So that means it's a kind of source for us analysis, for our analysis. For that I will just enable the term called sources term. Enable this. Just enable this. So once you enable that, so when you enable these options, you may have the option to re-edit these things. So right now I only enable the source term. So I'll click on source term. In which axis we have the momentum. So momentum is a kind of twisting. Okay. So here this axis refers to the z axis. Not z axis, it's y axis. This is z and this is x. So the rotation has happened on the about y axis. Okay. So I'll give the momentum on the y axis. Right now we only have one sources, but it says 0 sources. I'll change it. Just click on edit. Now the number of y momentum source is 0. I'll give it as 1, or else you can use this arrow to increase that. As soon as you enable this option, you may have an additional option to specify the momentum or anything. I'll change to, since it's a steady state problem, I'll choose to constant. Now you can enter the value. So I want to rotate in that clockwise direction, so I'll give the factor as minus 80 Newton per mm cube. So what does it means minus 80? So minus 80 means the momentum, the forces which acts in this direction, so which is in the negative y. So that is why I am giving the factor of minus. So if the blower will sucks the air from this side to this side, that is in the positive y, I can give a positive value. Okay, so that is the reason I will give the value as an active. So once you define that, just click on OK and say apply, click on close. Okay, so we just defined that fluid jet fan. So once you're done with that, the next thing is boundary condition. So this is very important. So in this case, we just assign the inlet velocity and then mixtures, composition, like how many percentages the oxygen is presented, how many percentages the carbon dioxide is presented. So that is what we are looking for. Just double tap on the boundary condition. Here you have a lot of things. So to view these things, what is symmetry? So by default when I choose that, so nothing will change over here. So if you want to view the symmetry or cold war or inlet fresh air thing, so you just select that. You'll have the option to view the things like highlighted zones. So when I enable this, now the Fluent has highlighted the region which I have selected. Okay, you can easily understand what is this region. Okay, this is inlet, and when I choose pressure outlet, this is outlet. So Fluent will highlighted that particular zone. So what is that? Wall jet. So this is wall jet, and interior fall region and symmetry. So car region, everything we can highlight it. Okay. So I will start from the velocity inlet fresh air. So just choose that. Make sure the type is set to the velocity inlet because the air is get inside from this region. So I'll just click on edit. So once I click on edit, so I need to specify the velocity, right? So we have the option to specify the velocity magnitude. So I'll give the magnitude factor as 0.8. So as per our problem statement, so the velocity of the inlet is 0.8 meter per seconds. And also you have the option to specify the turbulence. So want to reduce the turbulent ratio to 5 and the turbulent intensity is 5%. Okay. So once you define that, so by default the energy is enabled because we are working on a species. So we can specify the temperature of the inlet air, so that is surrounding air. Okay. So I'll just click on temperature. So by default it's set to 300 Kelvin. So it less than the 300 Kelvin. So I'll give the factor of 293.15. Okay. So the surrounding air or else the inlet air temperature is 293.15 Kelvin. Okay. So what is the ratio? That is species ratio. What are the components which is available in the inlet air? Okay, that is fresh air. So go to the species. So we initially defined 3 factors, that is H2O, O2 and N2. Okay, so we have to define that percentage. For that, I'll give a factor of the O2, that is 0.23. Okay, so once you specify the oxygen rate, that is 0.23, so just click on apply. So now we have created the boundary condition for inlet fresh air. Okay, so the next thing is we're going to do is pressure outlet. So choose the pressure outlet and make sure its type is set to the pressure outlet and just click on edit. Okay, so now we have to change the backflow turbulent intensity, but I don't want to change these options, so I can change to 5. And so I don't want to disturb any other options. I'll directly move on to the thermal, change the outlet thing. So this also specifies the outlet temperature. So I'll give the same temperature which I have mentioned in the inlet air. So that is 293, so 0.15. So 293.15. So once you specify the temperature, go to the species. So the same thing happens. So we only have the oxygen in that air at the initial stage. So I'll give the oxygen rate as 0.23. Okay. So I don't define any other factors like N2 or these things only comes from this car carry, from the car engine. Okay. So just click on apply and say close. Okay. Fine. So we successfully specified that velocity inlet and pressure outlets. So the next thing is mass flow inlet at the car firing source, that is from this region. Click on edit. Okay, so I want to specify the mass flow rate. So right now by default it's set to 0. I'll change to click over here and erase this value and enter the value as 0.1. And the direction specification, so it says directional vector. So I'll change to normal to the boundary. So that means the mass flow rate is perpendicular to the surface we have highlighted, and the turbulent intensity is set to 10 in this case. Okay. So also go to the temperature. So we know that at the car engine it has the temperature of around 1200 Kelvin. So once you specify that, go to species. So here we have H2O, that is around the percentage of 0.65, and N2, that is 0.35. So we don't have any O2 over here, so the O2 is spread around the atmospheric condition. So once you specify this region, this rate, so just click on apply. Say close. So we don't mention any CO2 percentage because CO2 is happened due to the combustion heat. Okay. So at this temperature of 1200 Kelvin, the nitrogen and then H2O is combined with that atmospheric air, it creates CO2. So we have to find the CO2 percentage in the air due to this combustion. So that is our that is our need to do this problem. Okay. So once you define that mass flow inlet car fire sources, we will move on to the next. Make sure just choose the symmetry. It's right to set to symmetry. Okay, we don't change any other settings over here, and we can set the wall condition. just choose the wall outer. So it's cement, right? So we have created a cement material, so we need to apply this material to this region for the surfaces. I'll choose the wall outer and click on edit. When I click edit, you'll have a momentum option, but I don't want to change anything over here. I'll directly move on to the thermal. I'll change the heat flux input to the temperature input. So by default it's set to 300. So I don't want to change that. So here you have the option to specify the shell condition. Just enable this. Now this edit option is enabled. So by default we only use one layer of the cement. I don't want to change that. Still, if you want to add 3 to 4 layers, you can. So just click on edit. You can give the number of layers and you can add so many materials for each and every layers. So my layer thickness is 0.15 meters. So the material is not an aluminum, it's concrete. So you can, if you want to define the heat generation rate, you can, but in this case I don't want to define that. I'll leave as it is and just click on OK and say apply and click on close. Now in that outer wall, the concrete material is applied. Similarly, you need to apply for the wall floor as well as the ceiling. Okay, so you don't need to apply for these things like inlet and then symmetry, because we already defined it as a inlet thing and then symmetry thing. Okay, only you need to specify the same thing for the wall, ceiling and wall floor. So instead of doing the work from the starting, what I'm going to use is a copy condition. So you may have the option called copy over here, right? So just click on the copy. By using this copy option, what do you want to copy? So I want to copy this property to which? I want to copy for the wall ceiling as well as wall floor. Okay. So remaining I don't want to copy. Okay. I want to copy the wall outer entire property to the wall ceiling and wall floor and say click on copy. You want to copy all the things? Yes. Okay. Now this value is entirely copied to these two things. So if you want to cross verify that, you can choose wall and say edit wall ceiling and go to thermal options. See, now the shell layer condition is automatically enabled. Go to edit option. So whatever we specified in that walls will automatically copy to these things. So it's a very simple way. So if you have a multiple boundary condition, so all you need to do here is you don't need to specify the properties for all the boundary conditions. So you can specify for one thing and then you can copy this entire value to that things. Okay. So yep. So once you define this boundary condition correctly, you can directly move on to the solution methods. I just minimize these things and double tap on the solution. Okay. In solution, go to the methods, but this time we don't use the coupled. Okay, so by default it's set to simple, so you can change to coupled. So once you change that, and you need to specify that operating condition. So go to the physics option at the top. You'll have the option called operating condition. Just choose that, or else you'll have the option here itself also. So you don't need to specify, change the operating pressure. I'll use as it is, but I need to add a gravity to this condition, the effect of gravity. Let's just enable the gravity. Okay, so the gravity is acted in the negative z direction. So I'll give a value of minus 9.81, that is meter per second square. So everyone know that value. And also I need to specify the density rate. Specifically by default it's set to 1.225. I'll change the value to 1.1989, or else you can leave that value also, it doesn't make any sense over here, and say click on OK. Fine. So once you specify that gravity, or else you can just enable the gravity from the general options also. The both things will do the same. Okay. So once you define the solution method, kindly change the pressure from the second order to the body weighted force. So in some cases, so we are looking on that volume region, right from the mass fraction of the CO2 So for that, body force weighted condition is much suitable. Okay. So the remaining options, I don't want to change that and just disable this pseudo transient option, because I am not going to use what is that, hybridized initialization. I only use a standard initialization. For standard initialization, you don't need to enable that pseudo transient. Okay, it's an advanced method. So for most cases we use, but in this case we don't use this option. Okay, directly you can move on to that solution controls. Okay, so in solution controls, I'll change the flow current number to 50. Okay, what does it means 50? Okay, you don't need to give a higher factor. Maybe you can give a little relaxation factor. We call it as a relaxation factor. So if you don't specify these values, like if you give a value of 0, so 100% of all the properties will be assumed. There is no relaxation factors which is involved in the convergence. That means it may increase your convergence process too complicated. So if I give a factor of 50 or 100, some relaxation may be done in the convergence process, right? From some assumptions may be made. So to make the problem more easier to solve. Okay, so I'll give the factor of 50. If you want to give a more number of values, you can give. So that is not an issue. And then you can also change some relaxation factor for the turbulence kinetic energy. Right now it's set to 0.8. I'll make it as 0.5, and also this also 0.5. So the viscous condition from 1 to 0.7. So if you reduce that value, probably your problem is get easily converged. Okay. Once you define that, you can directly move on to the monitors tab. So in monitors, you'll have a factors, that residual and report files and report plots. So I want to plot two things. So when it is get solved, you may have a different plots over here. So apart from the convergence plot, you'll have a weight masses, everything you can create from here itself. So how can I create that, sir? So we already discussed it in that previous session, but in this cases, we will also create some other things. Okay, just double tap on the these things. So first make sure in the residual, double tap on the residual, all the options like 10,000, everything is enabled or not. If it is not enabled, just enable this and say click on OK. And make sure also this option, print to the console and then plot, this option will be enabled or not. Okay. So double tap on the report plots. So I want to create a new thing, new. So new surface report. So that is mass flow rate. Okay. So I want to define a mass flow rate. So just click on that. So in which surface you want to view the mass flow rate? So I want to view the mass flow rate at the interior. Okay, so velocity. Okay, so I want to view the mass flow rate at the interior jet intake. So at this region, the center. Okay, so I will choose that. If you want to rename it, you can. So I'll name it as a mass flow rate. Okay, so I'll choose this and make sure a report plot, print to the console and say OK. Now it is get added, and after that I want another thing, surface, that may be a heat flux. So around these walls, for that, okay, I'm sorry, I'll change the type to integral. I'll name it as a heat flux. So, or else you can say it as an inlet heat flux or a heat flux anyways. So the variable should be wall fluxes. So the specification is total surface heat flux. Okay, so in which region you want to view that? So I want to view in that wall region. So to specify that region, I can choose wall ceiling. I want to view in the wall ceiling. Or else you can choose side walls also, but in my cases I only choose wall ceiling. So once you choose that, make sure report files and report plot, and print to the console and say click on OK. So now those two things will be added. Just click on OK. So I'll close it. Now our report generating process will be finished. So the next thing you're going to do here is go to the results, maybe initialization process. I'll shift over from the hybridized initialization to the standard initialization. I want to compute from the inlet. Choose inlet. Okay. So I don't want to change any other values. I'll just randomly click on initialize. Okay, it will take some time to get initialized. Okay, so everything is done. So the shell creation is also done. So once it is done, go to the run calculation. So before running the calculation, so you can save the case file of the problem. It may be useful for your future references. So if it is anything happens, any errors happen, you don't need to specify all the things from the first. So you have the case file. So file, so export, so case and data file, choose the data and say click on OK. So you want to overwrite? Yes, I want to overwrite because I already saved that file in that location. Now it is overwritten. Okay, so no issues. So once it is get saved, go to the run calculation. So I'll give a iteration factor of 2000. Okay, because it's a complicated problem, so which involves a turbulent flow. Since it uses a k epsilon equation, so it will take much iteration to get solved. So it is not possible to show all the iteration process in this video. So I'll just give the factor of 2000. Let's see whether it may converge or not. So I'll just click on calculate. Now the convergence process is get initiated. So you may observe over here. So the contours will be applied over here. So anyways, it will take some time to make the calculations. Okay. So as I said before, it may have a different, it may show you the different contours like heat flux plots and mass flow rate and your boundary conditions. So we clicked at that, what is that? Highlighted zones, right? So that is why we have a boundary condition highlight zones. So if you don't want that, you can close the tab also, or else you can shift over to the scaled residue also. So this is our standard thing. So all we need is the entire graph will goes below the 1 e power 6. So the software will consider it as a converged factors. Okay. So by default, we give a convergence as 2000. Okay. So once the 2000 iteration is completed, our problem is get solved. So otherwise, the problem is completed. Okay. So let's wait for that completion. So once it is completed, we'll check the results. Okay. So right now I will just pause this video. So till it's completed. So once it is completed, so the post processing, that is CFD post, will be a part 2 video. So in this part 1, so what we seen is, so how to define that boundary condition, right from the how to import that MHS file. So once you imported that file, so what is the first step I need to do in the Fluent module, and how can I specify the viscosity as well as the species condition, and how to define that materials, and once you define that material, how can I apply that material to the different boundary layers, right? The inlet velocity and then momentum, everything we have seen, and solution method, and also something related to the monitors, how to plot a different mass flow rate plots and heat flux plot in this console window. Okay. So that is all for this video, and we'll meet on the next video, that is CFD post, which is related to multi-species. Okay.